Recording.
Hi, my name is Ivy Liang,
And I'm Valentina Simon.
and today we'll be talking about the applications of linear algebra in facial recognition technology. Facial recognition is generally categorized into two different types of identification, one being open set and one being closed set. Open set just basically means that the computer or the algorithm is given a picture that it doesn't know whether it belongs in like the group or the pool of given photos. Basically, it doesn't know if the photo has a match or if it doesn't have a match in the pool of other given photos. So therefore, the algorithm would have to identify whether the given photo has a match or doesn't match, which you can see in the first row of this table. The second row of this table shows a closed set identification, meaning that the algorithm already knows that the given photo will match with one certain photo in the given pool. As you can see, the photo of the woman is matched with one other photo in the pool because the algorithm already knows that there is a photo, but its job is to find which photo it is. It does that by doing different types of, and then it verifies it, right? So then it'll just be like, oh, there's a match. Okay, I did my job.
This is the type of machine learning we're going to be using in this presentation.
So facial recognition also has a lot of real-world examples that we'll be talking about first before going into the more mathematical side of it. We've seen facial recognition a lot in today's society, most commonly being on different types of security applications, such as our iPhones. Because you see iPhones or any other type of phone, actually, they have fingerprint, they have password, but they recently also added in facial recognition as more of like another layer of security. And also in ATMs, they use facial recognition because ATMs contain obviously a lot of sensitive personal financial information. In addition, facial recognition is also involved in the law industry by helping recognize criminals in different types of public places such as stores or casinos or schools, commonly seen in video footages. And finally, facial recognition is used to find missing people, and over 3,000 missing children were discovered in 4 days using facial recognition in India. That's quite a big feat. Facial recognition is also commonly used in the medical industry. For example, it can help blind people recognize when others are smiling, using technology that kind of sends them a vibration by recognizing those facial expressions. It also can help diagnose diseases that usually have like a special facial change. For example, the National Human Genome Research Institute uses the facial recognition technology to detect the DeGeorge syndrome, which is basically there are like not mutilations, but there are changes to the face that can easily be detected through such technology. And with such technology, it helped diagnose around 96% of all such cases.
So now we're going to focus on the mathematics behind the facial recognition, and I'm just going to go into one primitive way to do facial recognition. There's much more advanced ways using machine learning that are currently being discussed, but I'm going to do a simplistic overview of some of the linear algebra behind a possible method. So in this method, the first thing we do is we get an image, and I'm going to call this image the unknown image, and we're going to see if we're going to have our image, and then we're also going to have a set of reference images. And so we're going to see which one of our reference images the unknown image matches best. And so the first thing that you do is you turn this unknown image into a matrix. And in this case, that's done by the potency of the blackness, right? So a darker black would be a larger number, and then white is 0 in this example. I'm talking about the image to matrix that's shown in step 1 on this slide. And then in step 2, we find the differences between the reference image and the unknown image. And so this is done by subtracting the matrices to see what the major differences are. And this is done between the unknown image and each reference image. So the next step is the Gram-Schmidt orthogonalization. And so this is an example of how the Gram-Schmidt orthogonalization would work for 3 linearly independent vectors. And you see that they are projecting each of the vectors such that they are orthogonal using projection, which is something that you're able to do with vectors. That's pretty easy to do. And then after they get all of their vectors into an orthogonal formation, they're able to do scaling in order to create a basis. So normally we think of in the basis of I, J, K, which has like 0, 1, 0, 1, 0, 0, and 0, 0, 1 vectors in the X, Y, and Z directions. And so this creates a basis that may not necessarily be those X, Y, Z, I, G, K directions, but instead it does have this orthogonal relationship between each of the vectors. And so what this paper does is it does this for n many vectors. So it just expands the method, and then it also does it for matrices instead of vectors. So it treats the vectors as it treats the matrices as vectors and does the projections and the scaling with those. And so it's done this orthogonal Gram-Schmidt method with each of the reference images. And so each reference image has its own unique basis. And then you're going to be comparing the unknown image in each of these bases. And that's how you're going to get the common matrix and the remain matrix. So the common matrix is, let's say we have the person Amy, and we have 10 pictures of Amy. So we're going to make a basis for each of the pictures of Amy, and then we're going to take the original picture of Amy, and we're going to subtract a picture of Amy times each of the basis projections. So here in this image, we had 3 linear independent vectors, and so then we get to 3 basis vectors. So here we would have 10 pictures of Amy, and then we would get to 10 basis matrices of Amy. And so we do a projection into each of those different matrices and subtract it from the original to get the common matrix. And then to get the remain matrix, we do the same thing with each of the bases we came up with, except we're doing it to the unknown matrix. And we want to see how large of a difference there is between the known matrix and the unknown, so between the reference and the unknown. And we compute this calculation for each of the reference matrices, and then we're like, okay, this reference matrix is the closest, this reference has the smallest difference to the unknown, and therefore this is the identification of that image. And so we're able to identify within a set. So there's a couple of setbacks with this. First of all, we may not have enough information. So if we don't have a large number of pictures of Amy already, we're not going to be able to identify another image as Amy. And then there's also the limit of only one threshold. So this only takes into account one type of error, which makes it statistically weak. And so it might make sense to use other types of algorithms, such as like machine learning based algorithms, in order to do facial recognition. So in conclusion, facial recognition is grounded in linear algebra concepts, and that's beyond this algorithm that I showed. Almost all areas of facial recognition are grounded in linear algebra. And it's a valuable tool in our technological society for both security and medical reasons. So it's really something worth pursuing, and it demonstrates how important applied math is to our society.